Okay, so we're working with this problem. We had this solid region E that was enclosed by a paraboloid and a plane. And so its boundary surface came in two parts. The paraboloid, which we're calling S1, and the disk that we have sitting on top that we're calling S2. Now, the boundary surface was oriented out. Now notice, out is going to look something like this. So for the paraboloid, out means away from the enclosed region. That's going to give me a downward, not necessarily straight down, except for this one point at the very bottom, but a downward orientation for those normal vectors. And then here, out away from the enclosed region is going to actually mean straight up. Okay, so those are my oriented surfaces, and I wanted to calculate the flux across each of these, add them up. We should get the same thing we got in the last video when we used the divergence theorem to calculate this as the triple integral over E of the divergence. I just kept our answer up here. It was 40 pi over 3. That's what we're really hoping we're going to get. Okay, so I'm going to just calculate, first of all, the double integral over S1 of f dotted with n ds. Now, because S1 is part of the graph of just z equals x squared plus y squared, I've got a really nice parametrization that I can use, just letting x and y essentially be my parameters. Now, if I were going to write out the parametrization, I would switch and say let x be u, let y be v, and then z becomes u squared plus v squared. But I'm going to use the shortcut that I've accidentally memorized what I'm going to get for the non-normalized normal vector that I'm going to dot with when I switch to writing things in terms of two variables. So I'm going to just keep things in terms of x and y. I'm going to say we'd be integrating over d. Now d would be the domain for this surface. That would be the projection onto the xy plane, which is just going to be this disk in the xy plane. That's actually the same disk that we got when we projected the solid onto the xy plane. So d is just a disk in the xy plane of radius root 2. Okay. But now I need to write my vector field f in terms of x and y only, because I'm using those as my parameters. So 2x can stay as 2x, 2y can stay as 2y, z squared becomes x squared plus y squared squared. Then I want to dot with the non-normalized normal vector. And because we've determined that we have a downward orientation, I know that in the z component I'm going to have a -1. And if I have a -1 here, then what goes in these parts are just the partials of z with respect to x and with respect to y. If it was upward, I'd reverse all the signs. This would be a +1, and these two guys would be negative. Well, z was x squared plus y squared, so the partial with respect to x is just going to be 2x, and the partial with respect to y is just 2y. Now, I'm probably going to ultimately want to switch to polar coordinates because I'm integrating over this disk. If I wanted to, I could have parameterized my surface in terms of r and theta from the beginning. I chose not to because I've accidentally memorized this. And so I was able to jump right to this without having to actually calculate the partial derivatives and take the cross product. Could have done that. It's going to be equivalent, but I find that setting it up in rectangular so that I can use this shortcut and then switching to polar after I've set it up is a little bit simpler. Okay, so I'm going to just work out what this dot product is, and then we'll go ahead and switch to polar. So I'm going to get 2x times 2x, that's 4x squared, plus 2y times 2y, that's 4y squared, minus x squared plus y squared squared. And now if I switch to polar, notice this is just 4 times x squared plus y squared, so that's going to become 4r squared. So we're integrating from 0 to 2 pi, from 0 to root 2, because remember we're on this disk of radius root 2. What we're integrating then is 4r squared minus, this is r squared squared, so that would be r to the fourth. And then dA, when we switch from rectangular to polar, that becomes r dr d theta. So let's just distribute that r. Integral 0 to 2 pi, integral 0 to root 2. I'm going to get 4r cubed minus r to the fifth dr d theta. Okay. So I'm going to just bump up to here, integral from 0 to 2 pi, but let's go ahead and take our antiderivative with respect to r. So an antiderivative of 4r cubed is 4r to the fourth over 4, which is just r to the fourth, minus an antiderivative of r to the fifth is r to the sixth over 6, and we're evaluating this between 0 and root 2. Now, this looks familiar because these were some of the terms that showed up when I set up the integral in the last video doing the divergence. So I'm feeling kind of good about that I'm seeing some connections. Okay, so let's see, this is the integral from 0 to 2 pi. Root 2 to the fourth is 2 squared, so that's going to be 4. Minus, we said that was 2 cubed, because each pair of root 2's gives me a 2, so that's 8/6 d theta. Let's see, that's 24/6 minus 8/6, so that's going to be 16/6. So we're integrating from 0 to 2 pi, 16/6 d theta, and of course that gives me 16/6 times 2 pi. Let's do a little bit of reducing. That's going to become a 3, so I'm getting 16 pi over 3. Now, that's not my final answer, but it's not supposed to be, because that was just the integral that I got over this first part of the boundary surface. So I'm just going to write in that I got 16 pi over 3 here. Now we still need to do the integral over S2, which is this plane. So I'm doing the integral along S2 of f dotted with n ds. This plane had as its equation z equals 2. Now, I can view that as a function of x and y, which is kind of nice. What this means is that I'm going to actually keep this for right now as the double integral over S2. Along S2, along that surface, z is just 2. So my vector field becomes 2x, 2y, 4. And I can see, just by inspection, that the unit normal vector is going to be 0, 0, 1, because it's pointing straight up. Now, I'm still writing this as my surface integral, because this really is, I've kept it in terms of S2 right here, and I can, because I actually found the unit normal vector. I didn't worry about parametrizing my surface. It happened that the z's dropped out because on this plane, all my z values are 2, okay? But I've still got this as a surface integral. I'm going to just show you how we can evaluate this and then how we could also switch to using a parametrization. This is the double integral over S2 of 4 ds, which is just going to be 4 times the area of S2, which is going to be 4 times pi times root 2 squared, because this disk up here also has a radius of root 2. So that's just 8 pi. So there was no need to actually even parameterize the surface because I ended up just integrating a constant. Okay. Now, if I had wanted to parameterize the surface, I could have done it using this as my parametrization. I could have said this is z being a function of x and y. So I could have said this is going to be the double integral over d of x and y are my parameters, so it becomes 2x, 2y, plugging in I get 4. Okay, so I get the same thing here. And then I would say, okay, this is oriented upward. So I know I want the z component of my non-normalized normal vector to be 1. And then what goes here is the opposite of the partial of z with respect to x and the opposite of the partial of z with respect to y. But if z was constant, both of those partials are 0. So even though I refer to this as the non-normalized normal vector, just by coincidence, it happens to be a unit vector in this particular case. And then we get dA. Okay. Notice that's exactly what I had here as a surface integral. Okay. It's just that I switched from S2, which was the plane up here. S2 was this disk in the plane z equals 2. D is that disk just dropped down onto the xy plane. So I switched to that. Then normally when I switch from ds to dA, there's some sort of a scaling factor. But that scaling factor is the magnitude of this vector, which happened to be a unit vector in this case. So the scaling factor in this case is just 1, and I can really sort of see that geometrically, because if I take this disk and I just drop it onto the xy plane, I'm not stretching it, I'm not shrinking it, I'm completely preserving its area. So the surface area that I get in 3 space is identical with the flat area I get when I project onto the xy plane in this particular case. So it's totally fine to keep it as a surface integral and just recognize that you're integrating a constant. It's totally fine to say I'm going to use my parametrization that z is a function of x and y and use the non-normalized normal vector, which just happens to be a unit vector in this case. So you could do this one either keeping it over S2 or dropping it down onto D. Really doesn't matter in this particular case. Normally, when we have a curved surface, it's absolutely necessary to parametrize and drop it down onto D. But in this case, because we ended up integrating a constant, I could just say it's a constant times the area of our surface. That works. Okay. So you'll notice what we got was 8 pi here. So what we have, if I add those two together, is 16 pi over 3 plus 8 pi. Now, if I find a common denominator, oops, not 8 over pi, 8 pi. If I find a common denominator, that's 16 pi over 3 plus 24 pi over 3. That is 40 pi over 3. And that's the same answer that we got when we used the divergence theorem. So we can be fairly confident that we probably did things right.